Now we are going to see the topic of singularity. So for that, first we have to see the definition of a regular point, then singular point, then isolated singular point, non-isolated singular points, type of isolated singular points. Okay. Then we move on to Cauchy residue theorem. Before that, I have to find the residue at pole. Then we can do the problem. One by one we will see it. Okay. First, the definition of regular point. What is the definition? Says that a point z equal to a is called a regular point of f of z if f of z is analytic at a. That means suppose I want to say a point z equal to a is a regular point. That means f of z is analytic at that point. Then I can say that that point is regular point. Okay. The singular point means a point z equal to a at which a function is not analytic, but every neighborhood of a contains at least one point at which f of z is analytic is called singular point. Okay, we will see the example. So this is f of z is z square. Okay. So what do you mean by analytic? So f of z is differentiable at that point, not only at that point, some neighborhood of the point also. So f of z is differentiable at that point and some neighbor points of that point. Okay. So suppose I consider f of z equal to z square. What is the f dash of z? 2z. For what value of z? For any value of z, f of z is always exists. Therefore, any point z is regular point for this function z square. Similarly, for take another example, f of z equal to e power z. The derivative is also e power z. So for any point z, f dash of z is exists. So clearly, any point z is called regular point for this function. Similarly, sin. Suppose I consider another function f of z equal to 1 by z. The derivative is minus 1 by z square. Okay. Suppose if we put z equal to 0, f dash of z does not exist. So that z equal to 0 is a singular point. Okay. The function, the derivative of a function at which, so the derivative of a function at z equal to 0 does not exist. So therefore z equal to 0 is a singular point. Okay. So simply I can say that f dash of z is exist at some point, also the neighborhood of that point, then we say that that point is regular point. So f dash of z does not exist at that point, but the neighbor of point f dash of z exists, that point is called singular point. Okay. Then next, isolated singular point. What do you mean by isolated singular point? A singular point A is set to an isolated singular point or isolated singularity of f of z if f of z is analytic in some deleted neighborhood of A. Simply I can say that isolated singular point means suppose z equal to A is a singular point, the neighbor of z equal to A, there is no other singularity exists, then we say that is called isolated singular point. Okay, clear? Okay, what do you mean by non-isolated singular point? The condition for isolated singularity fails, then the point z equal to A is called non-isolated singularity. Then type of isolated singularity. There are three types of isolated singularity. One is removable singularity, the second one is pole, the third one is essential singularity. We have to find the residue for poles. Okay, so we are going to find the residue for pole at poles only. Okay, we are going to only we find the residue at poles only. Okay, so I will explain later what I mean by pole, removal singularity, essential singularity. If anybody need, just send a message. Now directly I move on to method of finding residues. There are two type of pole is there. One is simple pole, another one is pole of order m. So if it is simple pole, what is your formula? So f real residue of f of z at z equal to a, the formula is limit z tends to a, z minus a into f of z. So f of z has a simple pole at z equal to a, then residue of f of z at z equal to a is equal to what? Limit z tends to a, z minus a into f of z. So alter method now no need. Okay, later I can explain. Okay. The next one is method of finding residue for a pole of order m. If f of z has a pole of order m at z equal to a, then residue of f of z at z equal to a, the formula is 1 by m minus 1 factorial, limit z tends to a, d power m minus 1 by dz power m minus 1 is into z minus a whole power m into f of z. Okay. Next we see some problems in residue, finding residue. So determine the poles and find the residue at each pole of the function f of z equal to z square by z minus 1 into z minus 2 whole square. First I have to find the singular points. How do you find the singular points? Making denominator equal to 0, the resultant is singular points. Okay. So what's the denominator? Z minus 1 into z minus 2 whole square, which is equal to 0. At what value of z the denominator becomes 0? Z equal to 1, z equal to 2. Therefore 1 and 2 are singular points. Specifically these are all poles. Okay. So the power of z minus 1 is 1, therefore z equal to 1 is called by simple pole. The power of z minus 1 is 1, so in your f of z, therefore z equal to 1 is a simple pole. And the power of z minus 2 is 2, therefore z equal to is a pole of order 2. Okay. So if you put z equal to 1, the denominator becomes 0, the power of the bracket is 1, therefore z equal to 1 is a simple pole. If you put z equal to, the denominator becomes 0, the function does not exist at that point. The power of z minus 2 is 2, therefore z equal to 2 is a pole of order 2. Okay. Now apply the formula. So z equal to 1 is a simple pole. The what is the formula? Limit z tends to a, z minus a, f of z. Very simple. Z minus 1, z minus 1 cancel. Just put z equal to 1, you will get the answer. Next. So I have to find the residue of f of z at z equal to 2. Z equal to 2 is a pole of order 2. That means in our formula, my a value is 2, m value is 2. So 1 by m minus 1 factorial, 2 minus 1 factorial become 1. So d power m minus 1 by dz power m minus 1. So d by dz, z minus a whole power m into f of z. So z minus 2 whole square into f of z. I can cancel z minus 2 whole square. Then apply u by v formula, then substitute limit z equal to 2, finally I can get the answer. Okay. So this is example for finding residues at simple pole as well as at pole of order m.